Okay, everyone, welcome to the final afternoon session. Our first speaker is O-joung Kwon, who will be speaking on a coarse Erdős-Pósa theorem.
Yeah, thank you. Thank you for inviting me to give a talk. Thank you, Rocker and Sangyeon, for organization. It's more or less about the graph theory things, but I will speak about the later on the Matroids things. Yeah, so this is joint work with O-joung Kwon from Kias and Pascal and Tony who are here. So here is an overview. So I will speak about variance of Erdős-Pósa theorem, so which is one of the classic theorem on graph theory, which tells about the packing and covering of cycles. And our result is about some distance variant of the Erdős-Pósa theorem, which was motivated from the recent development on the distance versions of Menger theorem. So we will see what that is. And then we also prove some partial cases of two related conjectures, and then I will talk about that later. Yeah. So first, I will introduce what Erdős-Pósa theorem says. So we are interested in the packing or covering the cycles in a graph. So what I mean by packing here is that we want to find the set of vertex joint cycles, as in the left-hand figure. And what I mean by covering is that you want to delete the vertices to kill all the cycles. Yeah. Yeah. So we are interested in the maximum size of packing and minimum size of covering. You can easily see that the size of a maximum covering should be a lower bound of the size of a minimum covering. Maximum packing is a low bound for the minimum covering, because once you have a packing, you have to delete at least one vertex from each of the cycles. You can ask whether there is some universal function f where that the size of a minimum covering is bounded by f of the maximum size of a packing number. This was what Erdős and Pósa proved. So they show that there is a function f of k, order of k log k, such that every graph either have a k vertex disjoint cycles, or you can kill all cycles by at most f of k vertices. Yeah. So is this clear? Yeah. So after Erdős-Pósa theorem, a lot of variations have been considered by considering another object, like dielectric cycles and S cycles, meaning that the cycles containing some fixed set of vertices, or cycles with some modularity constraint on the length, or cycles of length at least something, or group labeled case, or induced cycles, or even the Matroid circuit have been considered. The originally by Gillan, Gerard, and Herald, Whittle in the 2003, and then later Gillan and Cabell extended the result. But somehow the constraint on the distance between the cycles have been considered in some algorithmic world, but in terms of Erdős-Pósa theorem, it has not been considered much. Yeah, so I would like to introduce what distance packing means. So a set of cycles is the distance d packing if the distance between the two cycles is more than d. Yeah, so set of vertex disjoint cycle is just the distance 0 packing. So mostly we focus on the distance 1 packing, which we call as induced packing. Yeah. Some literature also says the induced packing. Yeah. Also, if you know the word induced minor, so this is just that the C3, the disjoint union of C3 as an induced minor, because so H is an induced minor of G if H is obtained from G by vertex deletions or contractions. So induced packing just means that you find the cycles where there are no edges between the cycles. Yeah. So starting from the original Erdős-Pósa theorem, we could think about that what if we change this vertex joint condition with the induced packing, right? So what if we replace the k vertex disjoint cycles with the induced packing of k cycles? Then you can see that this theorem no longer holds with any function, simply because of complete graphs. Because you have complete graphs, then you don't have any induced packing of two cycles, right? So any two cycles have distance at most 1. So you cannot pack by induced packing. But to delete all the all the cycles, you have to delete most of the vertices, right? So the bound, you cannot give a universal function f. But somehow that it's natural to consider the balls to hit the cycles. Just the deleting vertices is not sufficient, but maybe we can take some set and then consider to delete the balls surrounding the vertices. Yeah. So we define the balls here for a set of vertices S and an integer d. So we denote by BGSD as a set of vertices whose distance to S is m most d, as in the figure. So you have a set S, and then you consider the first neighborhood, and then the second neighborhood, and third neighborhood. The union of all of them is just the BGS3. And we say that it's a ball of radius d around S. So now we can ask a question that what you can say when G has no induced packing of K cycles. So is there always some small set S and some small number D such that the BGSD hits all cycles? I mean, by small is that universal for all working on the all graphs. Yeah. So as I observed by complete graphs, you cannot put D 0, right? Yeah. So D should be at least 1. Yeah. So here is our theorem. Actually, show that D equal to 1 works. So we proved that there is a function actually same order as in the Erdős-Pósa theorem, that every graph G contains either an induced packing of K cycles, or there is a set S of at most f of K vertices, such that balls of radius 1 hit all the cycles. Yeah. So this is our main result. And I want to remark 2 things. So the bound is optimal of the constant vector. And then this also implies the classical Erdős-Pósa theorem. Both statements can be verified by this simple reduction. So, yeah. So given a graph G, so let's consider a graph H, which is obtained by subdividing every edge exactly twice. Then you can easily see that any vertex disjoint cycles in G correspond to induced packing of cycles, because we subdivide every edge at least 1. Also, because we subdivide exactly twice, if you consider the balls of radius 1 to delete the cycles in H, so there is no reason to take a vertex, subdivided vertex, right? So it just, if you consider the balls of radius 1, then it deletes one another degree 2 vertex and one another branching vertex. So actually, it's more powerful to just delete the branching vertex. So this will correspond to just the vertex deletion to kill all the cycles in G. So there is an exact correspondence. So this theorem applied to H implies the Erdős-Pósa theorem for G. Also there is a known result. Erdős and Pósa also proved that the original Erdős-Pósa theorem, you cannot improve the function up to the constant vector. So that implies the first statement. Yeah. So at the beginning, I told you that this was motivated by a recent similar version of a Menger's theorem that people tried to research. Albert Schetten there and Georgakopoulos and Papaskolo proved recently that the statement that there is a function f such that every graph G with 2 vertices x and y, so you can find either a distance d packing of 2 passes, 2 xy passes, or you can find the vertex v whose ball of radius f of d hit all xy passes. Yeah. And then after then, both groups conjecture that this can be generalized to the k passes. So either you can find the distance d packing of k xy passes, or you can take k minus 1 vertices whose balls of radius f of d hits all xy passes. And interestingly, this was reputed by Nguyen and Scott and Seymour more recently. They even proved that when D is 2 and K is 3, so there is a counterexample. But the counterexample means that we really require the K minus, at most K minus 1 vertices. So they gave an example where the K minus 1 is not sufficient. For that conjecture, still, when D is equal to 1, it's open. It's an open problem. And then also, Nguyen and Scott Seymour proposed the more relaxed conjecture that there are functions f and g such that every graph either have a distance depacking of k xy passes, or you can find some set S of f of dk vertices such that both of radius g of dk hits all xy passes. Right? That seems to make sense. And I heard that many of groups tried to prove this, but still it's open. Okay, so I told you that our version, our induced version for Erdős-Pósa theorem. So what about the distance depacking? So we also tried to research that, but we couldn't prove for the general case, but we proved for the 2-cycle cases. So what it shows is that every graph contains either distance depacking of 2 cycles, or you could find 2 types of vertices, as you want. So S1 has at most 12 times d plus 1 vertices such that the both of radius 2d hits all cycles. Or if you want the both of, so if you want to delete the smaller vertices, but then the S2, the both of radius 3d hits all cycles. And then we conjecture, we propose a similar conjecture that there might be a function f of k and g of d such that every graph G contains either a distance depacking of k cycles or a set of at most f of k vertices whose both of radius g of t hits all cycles. Yeah, maybe we can relax that both f and k, f and g depends on the both k and d. But this is like a stronger form that we can expect. So we just say conjecture like this. Yeah. So this is the open problem. Yeah. So this is related to the recent conjecture on the tree independence number that I would like to briefly mention. Yeah, I think most of you know familiar with tree decomposition, that I do not put the definition of tree decomposition. The tree independence number of tree decomposition is defined as the alpha of every bag, where alpha denotes the maximum size of an independent set. So for computing the tree width, so we consider the size of a bag, right? But here we compute the maximum size of an independent set for each bag, and then this corresponds to the width of the decomposition. And tree independence number of a graph is defined as the minimum tree independence number over all possible tree decompositions. Yeah. So this notion is somehow natural because the maximum size of an independent set on bag is bounded by some constant. Then if you want to solve a maximum independent set, there are still the n to the c status to list up the possible solution on the back, and then you can efficiently devise the dynamic programming. So Dallard et al., actually including me and Sebastian. So we have some work on the tree independence number, and then we conjecture that if a graph class doesn't contain some star as an induced subgraph, and then exclude some planar graph H as an induced minor, then class has a bounded tree independence number. Yeah, so this is one conjecture by Dallard et al. And then our theorem implies that the conjecture is true when H is a k disjoint union of C3. The reason is that assume that we don't have KC3 as an induced minor, which just means that you don't have a K induced packing of K cycles. Then our Erdős-Pósa theorem tells that you have a small set S whose force of radius 1 kills all the cycles. Then you can easily see that we are assuming that the K1T induced subgraph free. Then for every vertex in S, the neighborhood has a small independence number, right? So summing up the overall the S, then still the BGS1 has a small independence number. And then the rest is a forest. So you can just take a 3D composition of WIS2 and WIS1, and then add the BGS1 to the all backs. Yeah. This gives a 3 decomposition of a small tree independence number. Yeah. So this gave us some algorithmic consequence, also proposed by Bonami et al. Bonami et al. Proved that the maximum independent set is polynomial time solvable on graphs with no induced packing of K cycles and no KTT subgraph. Yeah. So actually they proved that in that case, 3-WIS becomes logarithmic in N. And then you can do a dynamic programming. And then they pose a conjecture that maybe we can remove the KTT subgraph free condition. That just on the graphs with no induced packing of K cycles, you can solve a maximum independence set in polynomial time. Along the tree independence corollary, so our theorem tells that this conjecture is true for K1T induced subgraph free case. Because if then we have a bounded tree independence number, so we can solve a maximum independent set in polynomial time. Yeah, so left 5 minutes. I will talk about a few ideas on our theorem. So what we do is that, just for induced packing version, we recursively construct a subgraph whose vertices have degree 2, 3, or 4. And then want to say that if this construction has many vertices of degree 3 or 4, then you find the many cycles, and then this give what you want. This kind of argument has been used in the many other proofs for the Erdős-Pósa type result. But here, so we really want to ensure that what we have is an induced packing, right? For that reason, yeah. So we need to be more careful to add something recursively. Yeah, it's a little more complex than this. Briefly speaking, what we do is that so we have a current construction, and then we add some shortest possible H path, and then so we create the new vertices of degree 3 or 4, and then in the construction we take some vertices around the degree 3, 4 vertices. And then in the whole graph, we delete the neighborhood of marked vertices. So this will ensure that so we want to find the next one in the induced way. And then in the remaining graph, we find the next path and so on. And very briefly speaking, this is what we do. Yeah. So with a careful argument, this gives us some induced subgraph, which look like mostly that any packing of cycles is induced packing. But there is some technical issue that so one path might be that this green path where that their endpoints are adjacent. So this case is a little delicate because suppose that you have a much more larger construction and then you find any 2 cycles. Then maybe one cycles traverse like this and the other cycles traverse like this. Then there is an edge between the cycle, right? So we want to find an induced packing of cycles. So this might be a problematic. But we can observe that these special paths form a tree-like structure because one special path should be, so their endpoints only lie on the one of the previous paths. So so they cannot, so their endpoints cannot go to the arbitrarily. So if there are many special passes, then only looking at the special passes, you have some tree structure, and then those are independents that give induced packing already. So we can assume that there are a small number of special passes, and then ignoring special passes, the rest is mostly induced packing of cycles. Yeah, so this will give so our theorem. Yeah. Yeah. So here is a summary. So what it proves is that so we have almost the same as the Erdős-Pósa, original Erdős-Pósa theorem, that we find either induced packing of k cycles, or you can find the set S of size of k log k, whose Borel radius 1 hits all cycles. For distance d packing, so you can find the distance d packing of 2 cycles, or you can find the small set whose 2D Borel radius 2D or 3D hit all cycles. So our conjecture says that maybe distance d version holds with k cycles. Yeah. If this is true, that would be very interesting. Actually, this opens many open problems, actually. So we just consider the cycles with induced packing. So, but in the literature, Erdős-Pósa theorem has been proved to, or there are so many variations have been considered by considering other types of cycles, directed cycles, S cycles, and so on. What about their distance version, right? Yeah, all those problems are open problems. Yep, so I'm thinking about the S cycles or long cycles personally with some of the neighborhoods, but still there are many problems. And also we pose one more conjecture that looks to make sense, that generalize our theorem. Then maybe for every planar graph H, there is some function f and some constant d, such that either every graph G contains either kh as an induced minor, or you can delete at most f of k vertices. I mean, you can take at most f of k vertices whose Borel radius d hits all h induced minor. Yeah. So our theorem can be seen as a special case of this conjecture when h is a C3. Yeah. So I thought about the matroid circuits because Gillan and Cabell considered the Erdős-Pósa theorem for the matroid circuit, but somehow that distance constraint is like difficult to say because, right, what is the distance between the two elements? So I think some people consider that like 2 elements is the distance at most d. If there is a circuit of distance d, a circuit of size d containing 2 elements. But I'm not sure. Maybe there might be an analog of like this. But on the other hand, there are not much variations of a matroid circuit have been considered. For example, we may consider that you have some fixed set of elements, and then you can consider the matroid circuit containing a fixed set of elements. Would that have an Erdős-Pósa property? Yeah. That looks like an interesting problem to me, which I found yesterday, and maybe we can think about that. Yeah. So this is all, and then you can find our manuscript in the archive. Thanks.
Are there any questions?
Maybe for distance in matroids, instead of thinking about just a pair of elements, what's the shortest circuit that contains them? If you're looking at a collection of disjoint circuits, you could think about short circuits that meet 2 of the circuits. I mean, maybe that's, or maybe fail to be skewed to the 2 of the circuits or something like that. It might pay to think instead of thinking about elements, the whole circuits.
Yeah. Okay. Thank you.
Are there any further questions?
For the first theorem, the induced cycles in this packing, do you have, how big is the hidden constant in a big O?
It's slightly more than just the Erdős-Pósa theorem. So it's like Erdős-Pósa theorem, like a 4k, low k, something like that. So slightly better than you have to sum up the Fumer constant of k, low k, but it's not that big, I guess.
If there are no further questions, then let's thank our speaker again.